Hi class, the live stream didn't work, so I'm going to pre-record and upload later. This is a review of the 5 types of chemical reactions, something I already covered, but it doesn't hurt to repeat. There are 5 basic types of chemical reactions. There is synthesis, when 2 substances form one. An example of that is sodium reacting with oxygen to form sodium oxide. The reaction is balanced. You'll notice there has to be the same number of atoms on both the left and right side of the equation. So there's 4 sodium atoms on the left, there's got to be 4 sodium atoms on the right. You'll notice that the formula here is Na2O, sodium oxide. But there's 2 sodium oxides, 2 molecules of sodium oxide will give you the 4 sodiums that we find on the left. Then you have to balance the oxygens. There's 2 oxygens over here on the right side. There has to be 2 oxygens on the left, and they occur in the form of elemental oxygen. This is a synthesis reaction, but you could also, if the temperature was high enough and it produced flames, you could also call it a combustion reaction. If the sodium simply combined with the oxygen in the form of oxidation, then it would just be it would be a synthesis reaction. It sometimes happens that a reaction will fit into more than one category, so don't be put off by that. It can happen. Decomposition, when one substance breaks down into 2 or more. So in this case, potassium chlorate can break down to form potassium chloride and oxygen gas. You'll notice that I put little symbols after each molecule. That tells you its physical state. So in this case, it's a solid. Potassium chloride is a solid, although after this reaction, it might temporarily be a liquid for a short time because the reaction tends to evolve heat. And then the oxygen is a gas. This is a reaction that's typically used to support combustion. Potassium chlorate can be used in explosives formulations and in the rocket fuel. It's actually dangerous to use in gunpowder because it detonates too quickly. It can promote the formation of oxygen gas so quickly that it can turn a conflagration into a detonation. That's a whole other subject right there. But basically, the difference between a conflagration and a detonation is a conflagration is a very fast burn, whereas a detonation is the sudden breakdown of a molecule. And a detonation doesn't need oxygen. It can just happen if a molecule is unstable. The molecule will just violently break down, releasing a lot of energy. That's what high explosives are like. High explosives detonate, whereas black powder, the old-fashioned black powder that they use in the Bugs Bunny cartoons where you see Yosemite Sam blowing up because a barrel of gunpowder was too close to him and he struck a match. That's a deflagration where the gunpowder burns very quickly. But if you confine it, it can also look like a detonation. Anyway, those are decompositions. So decomposition can occur slowly or can occur very rapidly. And when decomposition occurs very rapidly, that's what they call it, a detonation. Double displacement. It means that 2 metals typically, it doesn't have to be metals, it can also be non-metals, but the example I've used is metals. So I showed you plumbous nitrate reacting with potassium iodide. The metals switch places, kind of like a square dance. They switch partners, and what you get is potassium iodide and potassium nitrate. The 2 remaining types of reactions are single displacement, where one metal cuts in on another. So in this case, I've shown lithium metal, a solid, cutting in on the copper in copper sulfate, replacing it so that you get lithium sulfate, and then the copper reverts to the metallic state. So for this to happen, the metal that's cutting in has to have a higher oxidation potential. It's something that you learn later on. Don't worry about that just now. But you'll notice that lithium is at the very top of the metals that can replace other metals. There's no other metal that can replace lithium because lithium has the highest oxidation potential, and that's why it's such a good metal for making batteries. The The other advantage that lithium has as a metal is that it's very light. It's the lightest, it's the least dense metal. So it's perfect for making batteries because it's both light and has a high energy density. Combustion is the last thing I want us to look at, and it's the fifth type of reaction. Combustion is used widely in our society. We use internal combustion engines to drive our vehicles. So we typically burn hydrocarbons in the presence of oxygen, and that creates heat energy and expanding gases which can be harnessed to do work and to drive the vehicles. The simplest combustion equation I can give you is the reaction between hydrogen and oxygen. This is what they used for rocket fuel to fuel the Saturn V rocket to go to the moon. They used liquid hydrogen, liquid oxygen, and the two fuels combine to form water, so it's a non-toxic combustion, doesn't produce anything dangerous, and it generates a lot of energy, obviously. The next level, you'll notice that I had a 1/2 in front of the oxygen because what forms is H2O. There's 2 hydrogens, 1 oxygen, so you always have to keep the reaction balanced. You can't have more atoms on this side than you do on that side. Whatever was here is still there, it's just been rearranged. And that's why you reflect it by, balancing the equation. You can't have atoms magically appearing or disappearing. The next 3 examples are examples of how you can balance a combustion equation. The first one is the reaction between methane and oxygen. So methane is a gas, they call it natural gas because it occurs in swamps, and it's usually even found in oil wells in the air bubble above most oil wells. There's going to be some compressed methane and ethane. So it occurs naturally, and because it's a very short hydrocarbon, when it burns, it only produces carbon dioxide and water for the most part. It doesn't suffer as much from the phenomenon of incomplete combustion as some of the other longer hydrocarbons do. For example, when you see a bus belching black smoke, the usual reason is because the fuel isn't burning completely. So some of it turns into soot because just the pure carbon is released into the atmosphere, and some of it turns into carbon monoxide because it hasn't had enough time to combine with oxygen, or there simply wasn't enough oxygen in the combustion chamber. So when you have incomplete combustion, you don't get only CO2. You might also get carbon monoxide, which is a carbon atom with 1 oxygen. Or you can sometimes even just get pure carbon, which is soot, the black smoke that you see coming out of the exhaust of a badly tuned bus engine. The reality is we're going to only balance complete combustion equations. We're going to assume that we live in a perfect world where all the hydrocarbons burn 100%, yielding only carbon dioxide and water. We know that's not true, but it would make for very messy calculations if you had to include the possibility of these 2 things are forming. In what proportion, for example, you would have to do experiments to find that out. So we'll just assume it's 100% each time. And you'll see how that works out in grade 11 and 12 when you get there. So anyway, when you want to balance combustion equations, you do it alphabetically. You start with carbon, then you do hydrogen, and then last of all, you do oxygen. So CHO, in the same order as the letters appear in the alphabet. That's how you balance combustion equations. It's always foolproof. You'll always get it right. Like I said yesterday, if it doesn't work for you, you get your money back. So methane plus oxygen. Let me show you how I did this. So there's 1 carbon on the left. That means you got to have 1 carbon on the right. So we're not going to write any numbers there for now. Then there's 4 hydrogens, but you've only got 2 hydrogens here, so we're going to have to put a 2 in front of the water to generate enough hydrogen. So now you have 4 hydrogens on the right, and you also have 4 hydrogens on the left. Last of all, you worry about oxygen. So there's 2 oxygens on the right plus 2 oxygens here, because 2 times the whole molecule, which each one of which contains 1 oxygen, gives you a total of 4 oxygens on the right. You must have 4 oxygens on the left. The only way that's going to happen is if you put a 2 in front of the O2. And that's now balanced. How did I balance this one? Let's erase the answer and we'll see. So propane is a gas that's used by plumbers to solder copper pipes. Soldering means you melt a lead tin alloy into the joint between the two copper pipes. There's three types of ways, by the way, of joining metals. One is soldering, the other one is brazing, and the third one is welding. So soldering melts another metal between the two metals. Brazing partially melts the surface of the metal that you're joining with another metal so that it forms a stronger joint. And of course, welding, you just melt the base metal and a filler rod so that they actually fully mix with each other. So welding is the strongest form of joining of two metals, but brazing comes out pretty strong too, and definitely soldering is no slouch either. But there are three different ways of joining metals using heat. Anyhow, propane is used by...
Teachers, please note that in case you haven't noticed, the internet is back on and you can access your Google Classrooms. Thank you.
Yeah, well, we did that already, and not going to trust it. So, the plumbers use propane to heat up metal to solder copper pipes because the temperature of the flame is sufficiently high. It's a compact. You can put it in a bottle about this big, and it liquefies when you compress it. So it's a perfect gas for soldering. It's also used in barbecue. The tank you use for barbecuing is filled with compressed propane. So it becomes a liquid when you compress it. And if you actually pick up your propane tank and shake it when it's full, you can hear the liquid sloshing around. And then of course when you open the tank and you let the pressure out, the gas liquefies as needed. Sorry, it turns back into gas as needed as it goes into the burner, and it undergoes the reaction that we're about to balance. So propane has 3 carbon atoms in it, so that means that there has to be 3 carbon dioxide molecules after the stuff burns, because the carbon atoms are still there, they've just combined with oxygen and been rearranged. The next thing is 8 hydrogens are present in propane, so you're going to have those hydrogens still present, but they're going to be in the form of water. So because water has 2 hydrogens each, we're going to put 4 waters, and that's going to generate the 8 hydrogens that were originally in the propane molecule. And now we're going to balance the oxygen. On the right side now, though, we're going to count the oxygen. So 3 times 2 here gives you 6, plus the 4 over here. So there's 10 oxygens mixed into the products of our reaction. So that means we have to put a 5 in front of the O2. So to burn 1 molecule of propane requires 5 molecules of oxygen, and will generate 3 moles of carbon dioxide. Sorry, 3 molecules of carbon dioxide and 4 molecules of water. And there's our balanced combustion equation for propane. Now let's do pentane. Pentane is an industrial solvent. I think it's used as a solvent for glue. When you want to stick, for example, the sole of a shoe to the leather, they sometimes will use a highly volatile solvent to make soluble the glue, so they can apply it quickly, and then it dries off, and then they stick the 2 things together, and there's your shoe. So pentane, if you burn it in the presence of oxygen, now you have 5 carbons to account for, so you're going to have 5 carbon dioxides forming. And now you can look at the hydrogens. There's 12 hydrogens in pentane, which means you're going to generate 6 water molecules. How did I get 6? Well, because each water molecule contains 2 hydrogens, and if you have 6 water molecules, there's your 12 hydrogens. There's no hydrogens in carbon dioxide, so I know all the hydrogen is showing up here. So all the hydrogen that was here is now in the form of water after the pentane burns. Now the last thing I balance is the oxygen. So there's 5 times 2 oxygens on this molecule, and 6 oxygens on this molecule, so 10 plus 6, 16 oxygens are on this side. So that means 8 oxygens had to be pumped in on this side, because whatever oxygens you find here, they were there before the reaction started, for it to sustain combustion. And that's it for today. So try to learn especially how to balance combustion reactions. I have other videos online you can look up if this isn't enough, but study what I did here and see if you can reproduce it. And I'll post